This is video 2.3. It deals with force. Once again, the key idea here is forces predict motion. If we know the force, we can work out motion. One of the most interesting parts of this is force multipliers, and this is incredibly useful, that we can take one force and we can increase it, multiply it. And we've got, via the principle of moments, we've got levers, gears, and via pressure we've got hydraulics. We also have the idea of deformation, and we're going to look at different kinds, elastic versus plastic. Springs in particular, there are a few equations, and the idea of a spring constant. So that's a number that tells you how a spring will behave. Over here we've also got the idea of energy again, gravitational potential energy, and that's force being applied against an object as it's given more height. So here we have the idea of deformation. Now if there's only one force, an object will accelerate or decelerate or rotate, but if we want it to deform we need two forces at least. So here we've got three, but on these two ones on the end, here we're stretching, we're compressing, and you cannot do that with one. Now here we've got elastic versus plastic. So elastic here, think of elastic band. They will return to their original length. So you apply a force here in the middle and it will return to its original length, providing you don't really massively overstretch it. Whereas plasticine, when it says plastic, think of plasticine. Here we've got little cartoon characters. Generally, if you give it a good push, it will extend and it won't return. It might shrink back a little, but it won't go back to its original size. So here we have springs. We have two key ideas here. We have length and extension. So length is the resting length of the spring when there's no force in it. Extension is the distance by which it gets longer. And the more force we apply, the more it will extend. Now for springs, this is a linear relationship or a straight line. We can see on this slide that it's not always a linear relationship. So elastic bands, because of the molecular interactions between these strands, will behave differently depending on how these strands are unfurling. We get a different level of resistance. So you don't need to know the detail for an exam answer, but you do need to know that not all extensions conform to a linear relationship. So here then we have the idea of a spring constant. So if we're investigating a spring, we would measure the force, we would apply force, and we'd measure the extension. And we divide one by the other to get this K. It comes from the German for constant. So what we're saying here is if we increase force, we'll increase extension, but it depends on the kind of spring you've got, the K, the value of K. So here we've got a very thick, strong spring, you're going to take a lot of force to extend it, and here we've got a much lighter spring, and we can see the effect here, and we're showing a big fat K there and a very thin K there to try and show the difference as well. So here we're looking at the idea of energy. So when we extend a spring, we all know what happens when you release a spring. There's going to be a release of energy. So how much energy we're talking about, how much work was done, if you like, to extend that spring. Now here we've added a word here. This formula we know from a previous video. Work is force times distance, but all along we implied average force. So here we've got a maximum force, let's say it's 10, and the minimum force is 0. So we've got 10 plus 0 divided by 2 would be 5. So that works for any situation, whatever the maximum number is. So divided by 2 is a half. So we've got work is a half force, remembering that's how we get the average force, times the extension. Now we can take that one step further here. So we've got these two formulas. We've got the force is a constant times the extension, and we've got the formula we've just discussed. Now we can substitute in here. We can take away this f here and put the kx here. That's the value of f, and if we tidy that up a little bit, we get x squared. So this allows us to work out the energy if we know the extension and we know the spring constant. Moving on then, we've got the idea of universal gravitation. It's a very weird fact, but all matter is attracting all other matter in the universe. It's usually only obvious when a very massive object, such as the Earth, is attracting us. And here we've got the space station going around, But the space station, like every other object, you, me, the space station, the Earth, has a gravitational field around it and will attract objects. So here we have the effect of being near or far from objects. So out here in space, the mass of this person with all his equipment hasn't changed. It's 100 kilograms. Goes to Earth, it's still 100 kilograms. It's the amount of stuff inside him, and likewise on the moon. But the strength of gravity in space is 0. On Earth it's 10, which is newtons per kilogram, and on the moon it's even less. So the formula here is W equals mg. So if we multiply this by this, we get 0, and so on. So we get different weights. So weight is a force due to gravity, and it varies depending on where you are in the universe. So on Earth then, we've said it's 10, and we need to know 3 things really if we want to know how much energy there is. We need to know the mass of the object, the gravitational field strength, and the height we're moving it through. So first of all, a bigger mass is going to result in, so these dashes mean it's not changing. Bigger mass is going to give us bigger GPE. Here, it's hard to show in a lab, or impossible to show in a lab, but increasing G will also increase GPE, so we get a larger GPE here as these identical masses rise on the Earth and the Moon. And finally, we have height. So if we move this object higher, we're going to have more GPE. Here's a worked example. So how much energy does it take to increase the altitude by 20 meters if mass is 4 tons? So we convert to kilograms. The board expects you to know the value of G. So we multiply it out, and there we get our answer. So moving on to freefall acceleration. Now on Earth this is 10 meters per second per second. If we ignore air resistance, all objects will fall at that rate. So the reason a feather falls slowly is because it has a greater surface compared to its weight. So that's why it falls more slowly, because it's far more affected by air resistance. So we can see that here, again ignoring air resistance, that although the mass is smaller, G is the same. Remember, W equals mg. So the acceleration, so remember acceleration is F over m, more force, more acceleration, more mass, less acceleration. So these effects exactly cancel out. So all objects, if you ignore air resistance, fall at the same rate. On the Moon, there is no air resistance, so all objects really do at the same rate there. So moving on then to moments. So it's a slightly strange word, but it just means a turning force, a turning effect. And they always involve a pivot. So we've got 3 pivots shown here. So here we've got the load pulling a nail out. Obviously there's some force here on the end of the hammer, and it's pivoting about this point here. Same idea here, we've got some load, a pivot, and then a force is being applied here. And finally, this is the 3rd class of lever. We've had the 1st and 2nd. Here we've got the pivot at the end, and the load is here, and we're applying the force there. So the key principle here is that a large force and a small distance can create the same moment as a small force and a large distance. And we say this is in equilibrium when there's no acceleration. So when there's no change or acceleration in the rate of rotation. So this one is, I've got it wobbling slightly, but you get the idea. So here we have a calculation. Again, we've got to be careful to adjust for prefixes. But this is a typical question. So they would give you, well, there's 4 key things here. We've got 2 forces and 2 distances, and they would give you 3 of the 4, and you rearrange the formula to work out your unknown. So moving on to gears then. So this is a little bit more complicated, so I'll slow down here slightly. On the left here we've got a moment again. So here's the pivot, the middle of this piece of metal here, the thread. Now the friction here, the red line here, is trying to stop it rotating. So it's a very large force here, but it's only acting over quite a small distance, and we've deliberately designed our spanner to have a very large distance. So this small force that we're applying here creates a big moment here, and we're able to overcome this friction. Now, in a sense, a set of gears use the same idea. you can think of this as being a spanner, and the bigger we make this blue cog, it's going to have more teeth, but that's a little bit by the by. The fact that it's a greater distance between its center and its edge means that any force we apply here will create a greater moment here. It can also work in reverse, and we can create higher speed with less force, but it's incredibly useful and used in a great many applications. So now we move on to pressure in liquids. Now the first thing to understand here is that pressure acts in all directions. It's very tempting to think it only acts downwards, but that's wrong. This little demonstration here hopefully makes it clear. If we had a bulb like this and we pierced it, we wouldn't be surprised to see water coming out in all sorts of directions, which tells us or shows us that, as we've said, the force acts in all directions. So here we've got a classic hydraulic system. Now, the key thing to understand here is that water or oil is incompressible, which is why these P's are all the same size. The pressure is exactly the same everywhere. Now you might say, oh, height will make a little bit of difference, but that's very small compared to the greater scheme of things. It's not being compressed is the key idea. So we apply a force here over a certain area and we create a certain pressure. Now the pressure here is the same, but as we can see, this big A, the area is much larger, so therefore the force we get out is much larger. Now again, we are not creating energy here because we are paying for this increased force by greater distance. So the energy is the same, but the distance here is greater, the distance here is smaller, but we're getting a greater force out. So here's a real life example, a jack. So here is the small piston. It's hard to see, but it is there, and that translates to the much larger piston. So with a small force over a longer distance, you can lift a car. So here we have a typical answer. Again, freeze it if you want to, pause the video if you want to see the detail. But in essence, we can work out the pressure here. So we've got area, we've got force, we can work out the pressure. We know the pressure must be the same here, and because we know the area, we can work out the force that's being created.